here. So we're going to look at number 1, part C. And I first want to draw your attention to what's at the top. Like order of operations, there is an order of transformations. And like order of operations, things that multiply would go before things that add or subtract. So you'll see that multiplying by a negative or multiplying by a number, so stretches and compressions or reflections, need to occur first, just like they would in order of operations, before you added or subtracted stuff, which is your translations. So that's kind of the order we're going to go through them. We're going to go through one set of transformations and see what the graph looks like visually. Okay, so this is what we want to understand about the transformations. How do they change the picture? So here's a random graph, some piecewise function that they put on there. We don't have an equation for it, but just by the notation that's here, we should be able to tell what's happening. I'm going to first take the equation and factor it. It has the reminder on there. Remember, the factoring is because if you don't factor, you'll be using the wrong h value, right? You won't see that correctly. So I'm going to rewrite this. It's this part inside of the function that has to be factored. There's just a negative that shouldn't be in front of the x if it's going to fit our format correctly. And when I factor out that negative, that parenthesis set where my x minus h belongs now looks like x minus 4 instead of x plus 4. It didn't change the number 4, but it changed which direction we would go for. Okay, so it's important we rewrite it like this first. So what do we have here? We have an a value of 1/2, and that would be called a vertical compression. That means it's going to take every vertical thing and however far it is away from 0, it's going to change the distance to like half the length that it used to be. We have a b value of -1. Because it's 1, there is no horizontal stretching and compressing, meaning it's not going to shrink in closer to 0 or expand further from 0 horizontally, but there is a reflection because of the negative. So there is a reflection here. That reflection is inside the function affecting x. When you change x, you flip over the y-axis. So this is a reflection over the y-axis. My h value is +4. If I didn't factor correctly, I would have thought that it was -4. And that means I'm going to shift to the right 4 units. My k value is -2, and that means I'm going to shift down 2 units. So now I'm going to physically go do this on the graph. I'm going to perform my reflections and stretches and compressions first, and then I'm going to do the shifting. Is this okay with everybody? I'm going to do them in multiple steps. I'm going to do them, then erase them, then do them again. So just let's get ready for that. I'm going to go ahead and do my reflection first. You could do the stretch or compression or reflection in either order, but they should be before the shifting. So I'm going to go ahead and I'm going to reflect the main points over the y-axis and redraw this figure. So pick something lighter like orange. So over the y-axis, so some main reference points for me. There's this point that's about at 2, 2. When I reflect that over the y-axis, that point is now going to be over here. Is everybody okay with that? The next point I'm focusing on is down here, because I want to draw this first I'm trying to draw this first segment, and I'm doing it by focusing on a couple key points that I can connect. So the next point here would get reflected over here. So this would be that first segment. What used to go right here has now been reflected over the y-axis and goes right here. Then I'm going to do the next portion. So for me, I'm now going to focus on connecting that last point I drew to make this segment, which connects right here. That point that's about -3, 3, I'm going to flip that over the y-axis. It would go over here. So there's that next segment. Lastly, I want to connect that point to this end point here, again by reflecting over the y-axis. So this looks like about -6 and then somewhere between -1 and -2. So it's going to flip over here to +6 Can you guys visually see the reflection? So the graph should look like it's just folded over the y-axis. I'm not good spatially sometimes, so I need to use these reference points to help me draw it. I'm not good at just like seeing what the whole thing would look like flipped. I like to do it in pieces. All right, next, so let's see, I did this. The next thing I'm gonna do is this vertical compression. So I'm gonna change the color again to something different, just green. I'm now gonna take all the points in orange. The graph in black, the original graph, doesn't matter to me anymore. I've done a reflection. I'm now gonna do a vertical compression. Remember that vertically, this is your 0. When you're vertically compressing, you're moving everything back closer to 0, a certain factor of its current distance. Because ours is a 1/2, we want everything to be half the distance that it once was from 0. So like when I look at this first point right here, currently, how far is that point from 0 vertically? 2 units. I want to compress it so that it's half the distance it was. If I take 2 and times it by 1/2 or divide it by 2, okay, if I take 2 and times it by 1/2, I would get 1. That point is going to be relocated here. What about this next point over here? How far is it away from 0?
3.
This one down here.
0.
0. If you're already on 0, your distance is 0. Doesn't matter if I multiply that by anything, divide it by anything, you're still going to remain a distance of 0. So this segment's now going to look like this. See how that kind of like compressed it back towards the x-axis? The vertical distance compressed. All right, what about this point up here? How far is that from the x-axis? What's our vertical distance?
3.
3. 3 times 1/2 is going to give me
1.5.
1.5. This now looks like this. Okay. Then lastly, this guy down here. If we want to be, and I'm okay with you guys doing this on this assignment, if you want to have called it -2, we could be a little, let's do that just for simplicity's sake. You can do the same. So let's like make this point end right here and have ended right here, just so we can say it's a distance of 2. But it's 2 below the axis, right? So when I compress the distance, it's still going to be below the axis. It used to be a distance of -2. I times that by 1/2. It's now going to be -1. So it's going to be like here. Can you visually see how the green graph is a vertical compression of the orange graph? As if you literally just took the graph and squished it from top to bottom closer to the 0, the x-axis. All right, now we can do our shifting because we've done all of our stretching, compressing, and reflecting. And if you're feeling pretty good, you can actually do all your shifting at once if you'd like. You can these together, like we did with our starting point with our greatest integer function. We can move every point right 4 and down 2. So if I start with this point right here, I'm going to move to the right 4 and down 2. Here's its new location. My next point here, I'm going to go to the right 4 and down 2. Here's its new location. So this blue segment that I just drew is exactly the same size as this one here and facing the same direction because there was no compressions or reflections, but it's just been moved to a new location by shifting left and right and up and down. So then I'm going to do the same thing with this point up here. I'm going to move it to the right 4 and down 2. So here, and then with my last point down here, I'm going to move it to the right 4 and down 2. And that is my final graph. So I am going to now erase this stuff behind it. Oh, don't erase you. So this picture is the original picture after it's been reflected over the y-axis, vertically compressed by 1/2, shifted to the right 4, and shifted down 2. Is that all right with everyone?
Yep.
All right. So it asks you to do 3 different ones with each graph, and there's 2 different graphs on the page to deal with. All right, let's look at the back. The backside says you're going to suppose that the point 61 is on some graph, whatever it's called f of x, okay, y equals f of x. So there's some graph, you don't know what it looks like, but you know that on that graph is the point 61, okay? So I'm just going to write it here, 61, to remind myself. They want to know what the new point would be and what transformation occurred based on the adjustment they make in the function. So let's say the transformation first, because we've been talking about that a little more clearly. So this is the change, that this function has this 3 inside of it multiplying the x. So is that in the category of reflections, stretches and compressions, or shifting? Stretches and compressions. Is it a horizontal or a vertical stretch or compression? Horizontal. Everything inside is horizontal. So I'm going to start with the word horizontal. And then think about how you use this number before you say if it's clearly a stretch or a compression. And think, if you have to, back to the greatest integer function. That's why we use that one for comparison, because you guys already know what happens. If a 3 was inside of the brackets for the greatest integer function with x, what would that do to the horizontal distance of your steps? It would compress them to 1/3. So even this is a 3, you're going to actually use 1/3. And this is going to be a horizontal compression. So then, does anybody know by arithmetic where this point would end up? We don't get to visually see it now, but if you're doing this horizontal compression of 1/3, where does 6,1 end up on the graph? Good. 2, 1. Who knows how she got that? Tyler.
So basically, when you put 6,1 into y equals x will be 6, and then y has to be 1, which means f itself is going to be 1, 6. And if you put f for 1, 6 here, you can plug 2 into x there, and then 6 times 1, 6 would be 1.
Good. Okay, so the 1 is unaffected, right? No vertical changing. The 6 will change because of the horizontal change. Think about how we did it on the graph. When a point was 2 above and we were trying to compress it by 1/2, what did we do with that coordinate of 2? We times it by 1/2, and that gave us the new coordinate of 1 or whatever. So in this one, your x coordinate is 6. This is a horizontal change, meaning my x coordinate is going to change. By how much? The distance it used to be from the 0, the y-axis, it used to be 6 over. It's now getting compressed by 1/3. A distance of 6 times 1/3 of itself, or 6 times 1/3, is going to equal 2. Okay? 6 times 1/3 gives me 2. The x coordinate's now 2. The horizontal distance has changed to only be 2. All right, take a few minutes in your group and see how many of these you guys can figure out. The most basic points that you could get for the parent function. Okay? The parent function doesn't have any shifting or reflecting or anything, so its turnaround point, its vertex point, is at 0, 0. So the most basic function of values for this point, we would want to plug in 0, and then to have a couple of points to guide us, we want to try and graph like 5 points. Because this graph turns around, so we want a middle point. We don't just want one on each side, because then people tend to not draw it with the right steepness. So if we could get 2 points on each side of it, this would be great. What are easy points to plug into something that's being squared? 1, 2, and on the other side, -1 and -2. This is how we build a parent function. We're just looking for the place we know something cool happens, like the vertex, the turnaround point. And we want a couple guiding points on each side of it, the simplest ones we can use. So we're a lot of times going to use -2, -1, 0, 1, 2, if the action is happening at 0, and those things can all be plugged in. So what do we get when we square these? When we square -2, we get 4, -1 squares to give us 1, 1 squares to give us 1, and 2 squares to give us 4. See how it's really easy to plug in these points? Because I'm not plugging them into a function with a bunch of transformations, right? I'm only plugging them into the most basic thing. I'm squaring stuff. That's all the plugging in we want to do. This is going to give us the most basic shape of our quadratic. So I'm going to plot these points. And this gives me a good picture of my quadratic. Now a little reminder about this list of characteristics before we actually use this new idea of transformations. What is the vertex of this quadratic? 0, 0. What is the x-intercept? 0, 0. What is the least amount of x-intercepts a quadratic could have? The least amount. 0. It could be shifted up, right? And then it wouldn't touch our axis at all. What's the most amount it could have? 2. So it's either going to have 0 or 1 or 2. So be aware of that, right? Because kind of like absolute value could have none. If the vertex was right, it could have 1. And if it crossed it, it had 2 with the parts of the v. What's our y-intercept here? What's the least amount of y-intercepts we'll have? 1. What's the most amount of y-intercepts we'll have? How many y-intercepts will we always have? 1. Because it extends this way and the parabola is always growing, it might be very skinny, but it is never straight up and down. It will always cross the y-axis at some point. So that is not a function. We're only studying the ones that are functions here. So we're only studying these ones that will have 1. You'll do that more, probably like pre-calc honors. We used to do conic sections in algebra 2. We swapped it out. Now we do all this transformation stuff. They do conic sections, and you'll get to do that in there. I miss it. I wish we got to do that. So our quadratic function only works this way. And that one, the y is squared. It's not a function, but that's a good question. All right, domain. What can we plug into this function? All real numbers, right? It doesn't have any limitations. You can see that on the graph. Or you can think about it. What numbers can I plug in and square? Any of them. What about the range here?
Y is greater than 0.
Since it's just squaring, it's zeros and positives because we can't square a number and get a negative, right? Or if we wrote that in interval notation. All right, a little review from your test. Increasing and decreasing intervals. So first, visually, if I start on the function from left to right, my first type of behavior is decreasing until the vertex point, and then I am increasing. But when I write it down, I'm not telling them how high I went or how low I went. I am telling them for these x's, these numbers on the x-axis, it is increasing, and for these ones, it's decreasing. So 0 is the turning point. And on this side of the turning point, all my x's were contributing to this part of the parabola, which I called decreasing. Over here, all these x's are contributing to this part of the parabola called increasing. If I'm only naming the x's, I would say that the x's that are lower than 0, so from negative infinity until 0 would be the decreasing part of the domain. And then from 0 to positive infinity would be the x's that are the increasing part of the domain. So if you were struggling with that, hopefully that will help you a little bit. So our decreasing interval was from negative infinity to 0. The negative infinity has to have a parenthesis. The 0 could have either. And then our increasing intervals from 0 to infinity. Oops. So this is a function. Thank you to Nathan's question. Okay, we already discussed that, and it is a function. Is it 1-to-1?
No.
No. So just like the absolute value, it doesn't pass that horizontal line test. Since it can't pass both of those relationships, it's not 1-to-1. The rate of change here for all the rest of the functions we study, we're not really going to ask you. It just varies because it's not a line anymore, right? It doesn't have this consistent, I always rise this and run this. All of a sudden it gets steeper or flatter. The axis of symmetry for this graph should be x equals 0. This graph has a minimum value at 0, no maximum value, and we're still not learning asymptotes yet. Seems really familiar, right? We will ask you all of these things about one of these functions. It's not going to be surprising, okay? So what are we doing with this? We're learning a new parent function. When we do parabolas, we want to know that we start with this little set of points right here. If I didn't remember them, would I know how to get them? I should. I should just quickly make the little X list and then square them all, making sure I have a couple numbers on each side of 0. How does that affect when our equation gets more complicated? All right? So what's happening in this equation based on what we were just talking about, transformations? We have an a value of 2. In words, what would I say that's going to cause my graph to do?
Vertical stretch.
Vertical stretch, specifically by 2, right? I have a k value of -4. Somebody besides Richard. In words, what is that telling us we're going to do? It's not a bad thing, Richard. It means I need to make sure other people know. Yes. Good. We're going to shift down 4. And then I have this h value in here. What is our h value? Is it +5 or -5? +5. And then someone new, what transformation is that going to mean that we have here? Yeah, go for it, Paul. Say it again, sorry. Good. This is going to be a shift right 5. Now, I color-coded these for a reason. Does anybody know why I wrote 2 of them in blue and 1 of them in red? What's different? Like, why are the blue ones grouped together? Then, like, the red one is not in blue. Why would I choose that those 2 should be the same color and this h value shouldn't be the same as them?
They're both targeting vertical transformation.
Good. So the ones that I colored in blue are targeting the vertical change, right? They're changing something in the vertical measurement, where the one that I wrote in red is changing something in the horizontal measurement. Okay? So what I'm about to do, I don't know how you guys are going to feel about it. We're going to see. I'm going to write down our parent function first. So I do want to start with the parent function every time. So I have this memorized, but we know how to make it very quickly. I'm just squaring these really quick to get those numbers. This way the squaring is done. Is everybody on board with me that if I start with these numbers, I've already done the main thing this function does, which is like square stuff? And now I want to take this picture that we basically got of all the squared stuff, and I want to do the thing that you guys said to it right here. But doing it with the picture in the little homework paper was annoying, right? Was it a lot easier to do the points on the back? So that's what we're going to do, except for instead of picking one point like 6, 1, we're going to use this collection of parent points right here, and we're going to change them all to what they would be in their new version. All right? That means when I make this new chart, the x is only adjusted by the stuff that I wrote in red, like Scott pointed out, right? That like horizontal is happening inside of there and the other ones are vertical. So what's the only thing that's going to happen to the horizontal distances? They are going to shift right 5. What type of operation or arithmetic would you guys have done on the back of that homework 1 handout if you wanted to shift the point right 5? Addition to which coordinate? The x coordinate. So the x coordinate is going to get a +5 to all of them. And I'm going to make a new list of x's. I am not plugging into my function. I've already done all the plugging in by doing the squaring. I'm just going to take each thing that was here. This used to be -2. Guess what I'm going to do to it? Add 5. That's going to move it to the right 5. And now instead of sitting at -2, it's going to be at 3. -1 is going to get shifted to the right 5, and it's going to be at 4. 0 is going to get shifted right 5. It's going to be at 5. You guys get the point? Okay. That's the only horizontal thing that happened. So I can just do that just to the horizontal parts of the points. We've separated the points into like this measures the horizontal thing and here's all the things that happen to them and then here's what's happening to the vertical ones. So then I have to do some vertical stuff. The vertical stuff needs to happen to the y's. There's 2 things happening. There's this vertical stretch by 2. How do I do that? How would you guys have done that with your point? With the point 6, 1, if it was vertically stretched by 2, what would be the new value for the point? Tyler? You'd multiply it by 2. Which part of it by 2? The y. So they get multiplied by 2. But it also has something else happening. It has a shift down 4. So what other operation has to happen to the y values of these points? Zach? Minus 4. And it does them in the right order of operations. Beautiful. Because what's it going to do first, the multiplication or the subtraction? Multiplication. And what did our worksheet say first when we were looking at the visual? You had to reflect and stretch or compress first, and then lastly, shift. And so that's what we see happening. So what's going to happen is each of these y values, so the first one is 4. 4 is going to get multiplied by 2 and then shifted down 4. So it's kind of weird because it ends up in the same place, but that doesn't always happen. So 2 times 4 is 8, and then minus 4 is 4. All right. Then it's going to happen to 1. 2 times 1 is 2, minus 4 is negative 2. Then it's going to happen to 0. 2 times 0 is 0, minus 4 is negative 4. Then it's going to happen again to 1, but I already did that one, and again to 4. Ready? Plot the points. Let's see if we did it right. Moment of truth. If you're struggling with the difference between, like, how do I even know how to connect them, remember that middle point was your vertex. It's been transformed to 5, negative 4. That should be our new vertex. And then just ask yourself, does it look right? Does it look like the vertex ended up in the right place? Yeah, based on our h and k that are always like our starting point, that seemed right. It's facing upward. Should it be facing upward?
Yeah.
Yeah, it didn't have any sort of reflection to face it downward. It looks a little skinnier than our normal parabola. Does that make sense? Yeah, because it was like stretched vertically by 2, right? So it's causing it to like get more of that upward stretching is making it look a little skinnier. Okay. All right, so what we're going to have you guys do, we're going to have you guys try to fill in the characteristics except for the x-intercepts. We're going to save those for later. So actually, no, we're not. Try it. In this format, we're going to do them now. In other formats, we'll do them later. So why don't you guys take 5 minutes, see how much of the characteristics you can get done, and then we'll go through those responses, and then we'll look at the problem on the back. All right, I'm going to do the intercepts last, but go through some other things. So our vertex, notice it says h and k because those values do give us our vertex. It should be at 5, negative 4. Our domain should be all reals. Our range is that y is greater than or equal to negative 4. Our increasing interval is from 5 to infinity, and our decreasing interval is from negative infinity to 5. Make sure you are using the x values to explain those, not the y values. It's not one-to-one. You're not going to be asked about the rate of change since it varies. Your axis of symmetry should be at x equals 5. Your minimum value should be at negative 4. There is no maximum value, and we are not doing asymptotes. I haven't gone through intercepts yet. Are we okay with the rest of the information up here? Any questions about those characteristics? All right, let's talk about intercepts. All right, for a y-intercept, our equations are set up where y equals, so you basically can just plug in as long as you do order of operations right and find the correct y-intercept. You're always plugging in 0 for x because a y-intercept is a point on the y-axis, therefore it must have 0 as an x value. So when I plug that in, it would look like this. Order of operations says I would do the operations inside the parentheses first. I would do that exponent next. Negative 5 times negative 5 is 25. Then I would do multiplication and division before I do addition and subtraction. So this would be 50 minus 4 or 46. And I heard a good conversation at this table up here about, like, it seems ridiculous, like 46. And then the problem was like, but look at it, right? Look how steep this gets. Does it make sense it might not hit the y-axis up until positive 46? It does, because it's been moved way over and it's really steep. Okay? So my y-intercept, we write our intercepts like points. I'm going to request that you do that on your test from now on, okay? There's just a lot of things that we're asking you guys about, so we like to see the right note. If it's a line, it has to be a line equation. If it's a point, we want it as a point. So X-intercepts. A little trickier because X is buried in the equation. I know to make y equal to 0 because every x-intercept is on the x-axis, which means it's a point where I know we have 0 for y. The question is, how do we solve this? So you start the same way every time for every function. When this was an absolute value equation, the first thing we focused on was getting the absolute value alone. So you want to do the same thing here, but you're just getting a quadratic alone. So you first want to get this, because it has all the x's inside of it already, alone. So I'm going to add 4. Oops, sorry. And then I'm going to divide by 2. Now, when we got here with absolute value, the way we got rid of, I'm using that really loosely, okay, the absolute value was to understand what absolute value meant, and that meant that stuff inside could be equal to this positive version of the number or the negative one. We wrote 2 equations and we moved on. This is where it gets different for each function, because each function is going to have something unique about it at this point. Is it a squared? Is it a cube? Is it a radical? Is it a cube root? Is it an absolute value? What do we do when we want to get rid of this? I don't want that exponent of 2 there, because if it wasn't there, I could just add 5 and be done with it, and x would be by itself. Good. We're going to use its inverse operation, which is a square root. Let's see if you guys remember this. When you square root both sides of an equation, there's something really important you have to remember. Let's say I gave you guys this equation. I could solve it the same way that you guys just said, right? Okay. That answer is not right. Completely. You say it verbally. I gave you an equation that said there's a number, and when you square it, it's equal to 4. What is the number? There's 2 different numbers, because before it was squared, whether it was positive or negative, you don't know. The squared took it away. So when you square root it, it can be either. Okay. All right. So when we're square rooting this, we're getting square root of 2 over here, but it could have been a positive or a negative square root of 2. We just don't know. Both of them work. Now that I have x released from the squared, I can do the final arithmetic to get x alone, which is to add 5. And don't be scared of this. I know it's really ugly, but it's actually very quadratic formula looking, because we're dealing with quadratics. I can't combine all of that together because one's under a radical, one's not, whatever. This is how I'm going to write it. It's a 5 plus or minus the square root of 2. This is actually 2 answers. One x-intercepts is when you take 5 and add the square root of 2 to it. The other one is when you take 5 and you subtract the square root of 2. Does it make sense that I should get 2 x-intercepts for this problem?
Yes.
Look at your graph, right? It's going to cross the x-axis twice. All right, are we going to remember to plus or minus every time we incorporate if the square root is just there, if I just say, what is the square root of 4? Don't tell me plus or minus 2. No, the square root of 4 is 2. Because when I say square root of 4, what is it implied that's in front of that square root if I didn't say anything was there? A positive. If I say the number 8, it's implied that it is a plus 8, right? Okay, so square root of 4 is 2. That doesn't change how you've done math. But when the number was squared and you only know the outcome, in other words, when you use a square root on both sides, you have to consider both possibilities because it's a mystery. It could have been either. Okay? So when you square root both sides of an equation, you should plus or minus. All right. Are we good? All right, turn the paper over. Welcome to Algebra 2 Trig instead of Algebra 2.
Wait, hold on.
Yes.
So, in the X-Intercepts, can't we just write 5 plus negative?
Plus or minus. You can write it as 1 point with a 5 plus or minus -2. Or a square root of 2, sorry. All right, first thing. We need to rewrite our function in the format, and that 1/3 sitting in front of x doesn't do us any good as far as seeing our x minus h quantity. So I am going to rewrite this, and inside that squared, I need to separate the 1/3 from the quantity that's going to contain x, just like you guys did with your greatest integer function, right? This is how it relates to that. We're doing all the same things. What is left in that parentheses when I factor out a 1/3? I didn't factor it all the way out of the squared, but what would be left in there? X plus or minus? What do you think? Plus, minus, plus, okay. And what's the number? 3. So either some of us are just really good at fractions and we know 1/3 times 3 is how we made 1. And if not, it's the same thing we talked about before. It was a 1. You factored out a 1/3. If you go through the motions of dividing 1 by 1/3, you will get 3. So we have an a of -2, a b of 1/3, an h of -3 or +3? -3, and a k of 5. Words to describe what's happening with these values. Because a is negative, there's 2 things happening with a. It controls 2 things. It controls reflecting and also stretching and compressing. So because it's negative, there's a reflection over the x-axis. Because it's 2, there is a vertical stretch by 2. B is 1/3, so no reflection there. It's a horizontal, do I want to say the word stretch or do I want to say the word compression? Stretch, because it says 1/3, but how are we going to use the 1/3? As a 3, okay? So this is going to be a horizontal stretch because I'm going to be multiplying things by 3. My h value being a -3 means I'm going to shift to the left 3. And my k value being 5 means I'm going to shift up 5. All right, so I'm going to make a table. And I'm going to make all these things happen. The first table I'm going to refer to is my parent function table. So this did all the squaring, right? Every time I do a quadratic, I'm making this little easy table. That's not my function, that's just the basic squaring function. My function took that basic squaring function and did all this crazy stuff to it. So now I'm going to take all those points and do that same crazy stuff to them in the form of arithmetic, so I don't have to draw it 600 times and do all the transformations. Okay? So how am I going to do that? For x, this is horizontal and this is horizontal. I'm going to stretch it by 3. And I'm going to shift it left 3. So I'm going to times it by 3 and then subtract 3. That means I'm going to take every x in that table and do those operations to them. -2, I'm going to times it by 3 and subtract 3. That's going to give me -9. -1, 0, 1, 2. They all get transformed to these numbers by taking each x value, timesing it by 3, and subtracting 3. Then I'm going to do all my vertical stuff. My vertical stuff is here and here. A reflection and a stretch both multiply the value, because multiplying it by a negative will change it from a positive to a negative or a negative to a positive. So I'm going to have negative 2y, and then plus 5 because it's going up 5. I'm going to take every y value in that original list of things that were squared, and I'm going to transform it with these transformations using arithmetic so I don't have to draw them, okay? So I would start with 4. Negative 2 times 4 is negative 8, plus 5 is negative 3. Then 1, 0, 1, and 4 again. And then I'm going to plot them and hope it looks the way it should. I expect it to go the other direction, facing down. I expect it to be a little bit stretched out each way, so I don't know how that will quite work, and shifted. So let's see if I'm right. I'm plotting. I just can't count and talk at the same time all the time. Looks pretty good. Looks like it was shifted over. It's facing the wrong direction. And I'm not too concerned that it's a little more wide than it is narrow. At first this 2 might make me think it should have been narrow because it was vertically stretched, but it was horizontally stretched out more than it was vertically stretched out. So that probably makes it overall appear a little wider. And then we will do the x-intercepts of this together and the y-intercept. And then I'll just post the answers for the rest of it that you guys can get from there, because I think we've gone through the other parts thoroughly enough. So I'm going to go through the x-intercepts first. It doesn't matter which version of the equation that you use. So I'm just actually going to use the very original version of the equation. It's just going to be ugly though. All right, so the first thing I'm going to do, are you guys okay with this? Because I'm going to try to write it in one step. We normally don't write out every step like we've been doing, but I know our algebra skills needed a little, it's been a while, We're going to subtract 5 and divide by negative 2. So eventually we have it look like this. Okay, you subtract 5, you divide by negative 2, you get a positive 5 over 2. All right, what do I do next? Richard?
Square root both sides.
Good, I square root both sides. What do I want to make sure that I include since I square rooted both sides? Plus or minus, right? This number over here can be either positive or negative. And I'm going to write it a little different right now, but that radical extended over the entire fraction, so it's in the numerator as well as the denominator. I wrote it like that so you guys don't forget. I've been watching you guys, and sometimes you have it written like that, and then it just like disappears from the denominator part like it was only over the numerator. What do I do next? No, someone else different than Richard. I like it, Richard, but I got to make sure the rest of them know. And Tyler, someone else. What do we do next? We're just trying to get x by itself. Nathan. Okay, good. We're going to subtract 1. And then we're going to times everything by 3. Please be careful when you times everything by 3. This 3 on this side needs to distribute to both of these terms. Okay? This is basically our answer, except for, you know how there's like grammar rules in English? We have them for math, right? We don't generally leave our fractions in this irrational format where there's like a radical in the denominator. Do you guys know how we get rid of that radical in the denominator? Ben?
Transfer rad 2 into rad 10.
Good. Technically, we're multiplying top and bottom by rad 2 because what that does is rad 2 times rad 2 just becomes 2. And technically, this is considered more proper. It's the same number. If you type them into the calculator, they're worth the same thing. But just like English grammar rules, math has them too, and generally we don't leave that irrational part in the denominator. So my x-intercepts are 2 points. I can write them separately, or I could write them like this. I'm okay with this, but are you guys understanding that that's 2 points? Okay, yeah, it's ugly, I know. Yep, that's how you're gonna be expected to do it too. We're gonna use the calculator in here for purposes of solving things that are more difficult for us to solve on the graphical interface. We are not going to use it in here just to turn everything into a decimal. We have to remember how these algebraic things work. Okay, all right, I will